Hello everyone, this is Himabindu from the Department of CSIT. Today in this video, I would like to explain about the concept called pushdown automata. So here, what is meant by pushdown automata? In previous videos, we discussed about the grammars like regular grammars, and we discussed about the languages and these regular languages which are accepted by the finite automata. Like that, here this we are discussing about the pushdown automata. So which type of languages should be accepted by this pushdown automata and which type of grammars are accepted by this pushdown automata, we will see. Here, what is meant by pushdown automata? So pushdown automata is a way to implement a CFG, context-free grammars. So here in previous videos, we discussed about the context-free grammars, like we are minimizing that context-free grammars, how to construct a context-free languages, and how to convert from one normalization form to another normalization. So these are all the topics we already discussed in the context-free grammars. So here we are talking about the pushdown automata. So the automata which is accepting the language called context-free grammars. So here in the previous videos we discussed about the Chomsky hierarchy. So in that one we have four types of grammars we have. For every grammar there is a language acceptance, and we have also the automata. So which languages are accepted by the different automatas. So we are discussed this all the topics in the previous videos in the Chomsky hierarchy. Now I will summarize this Chomsky hierarchy to know about which type of language is accepted by this pushdown automata. So here we have four types of grammars. So here this pushdown automata which is accepted by the grammar 2. So here the type 2 grammars we have. So the type 2 grammar is nothing but it is a context-free grammar. So context-free grammar it is. And what type of language is accepted by this pushdown automata is context-free language. Context-free language. So this is a type 2 grammar, and this is the pushdown automata which is accepting the grammars, context-free grammars, and the language which is accepted by the pushdown automata is a context-free languages. So here this comes under the type 2 language. Let me summarize the hierarchy. So type 3 is nothing but it is a regular grammar. So type 3 is regular grammar. And language is for this type 3, we have the language regular languages. And which type of automata it is accepted by this type 3 grammar? So it is a finite automata. So and coming to the type 2, we already discussed. So in type 2 grammar, we have the grammar context-free grammar, and the language which is accepted by the pushdown automata is context-free language, and the automata is pushdown automata. And the type 3 finished, type 2 finished, and type 1. So in the type 1 grammar, we have the grammar which is accepted by this automata is nothing but context sensitive grammar, and the language which is accepted by the here we will write the automata. So which type of automata accepted by the type 1? So it is a linear bound automata. So for this automata, the language which is accepted by this type of grammar is context sensitive. So context sensitive language. So here the grammar which is accepted by the type 1 grammar, so it is a context sensitive grammar. So this is about the type 1 grammar. And here we have the type 0 also. So here type 0 which is the language which is accepted by this enumerated language, recursive enumerated language. And Here the automata which is accepted by the type 0 is nothing but Turing missions. Turing missions. So here these are all the Chomsky hierarchy. So in this one we have a 4 types of grammar. In this one we have the type 2 grammar, so which is represented as a pushdown automata, which is accepted by the language and grammar, context free language and context free grammar. And coming to the pushdown automata, it is a so here we designed a DFA. So DFA is nothing but discriminate finite automata. So that is nothing but which comes under the finite automata. So finite automata which is having the language, regular language and regular grammar. So here this discriminate finite automata which comes under the type 3 grammar. So type 3 grammar. So in this one, we have the discriminate finite automata. So with that one, we will generate a regular grammar. So here a DFA can remember a finite automata of information. So here we will say that it is a finite amount of information should be remembered by the DFA, discriminate finite automata. But in PDA, pushdown automata can remember infinite amounts. So here there is a difference. So from type 3 to type 2 grammars, we have a somewhat variation. So what is that variation in the sense? In finite automata, we have a finite amount of memory is there. And when coming to the pushdown automata, we have infinite amount of information should be there. Remember, we can remember infinite amount of information in the pushdown automata. So there is a type 2 and type 3 difference is there. So what type of difference it is in the sense the two, it can remember infinite amount of information with the pushdown automata. A PDA is more powerful than FA. So FA is nothing but finite automata. The PDA is nothing but pushdown automata. So why we can say that it is a powerful in the sense it can remember infinite amount of information. So any language which can be accepted by the finite automata can also accepted by the PDA. So we can say that it is a subset of PDA. So a finite automata is a subset of PDA. PDA is nothing but pushdown automata. So here FSM is nothing but finite state mission. So generally this pushdown automata, it is a combination of stack with the finite automata. So finite state mission. So here we can remember in PDA we can remember infinite amount of information. So how this infinite amount of information is stored? So we can say that along with the finite amount of information we can store in the stack this infinite amount of information in the stack. So we can say that so finite state mission has a very limited memory but PDA has more memory. So here we can say that the PDA is nothing but a finite state mission with the stack. So here only a finite state mission has a limited memory. When we add that stack to the finite state mission, it is called a PDA. So that is the difference. So here why it is a PDA is more powerful than finite automata in the sense it is having the stack. So in that stack we can store infinite amount of information. So these are all about the Chomsky hierarchy and what is meant by a PDA, pushdown automata, when coming to the compare with the finite automata. And what is meant by stack? So what this stack contains? So here what are the operations involved with the stack? So here the general definition of pushdown automata. So when we are giving the input string, we will give that input string to the finite control unit, whether the string is accepted or rejected. So this entire thing is a finite automata. So here this comes under the type 3. So type 3, the type 3 grammar which is accepted by the finite automata. So in that one we have a finite state mission and for that mission we will give the input string and finally we will get that the string is accepted or rejected by this finite automata or not. We will check. So this is the type 3. When coming to the pushdown automata, we are including a stack to the finite automata. So here one more element is added here for the finite state machine. So that is nothing but PDA. So when we combine this stack to the finite state machine, it is called a type 2 grammar. So type 2 grammar, which is called PDA, push down automata. So here this stack which is having filled with the stack symbol. So here in this stack we can give the input symbols. We can give the input symbol along with the initialization. We will discuss more about this stack in the definition of pushdown automata. So here when coming to the finite automata, we are adding the stack to the finite state machine called a PDA, pushdown automata. And here what is the stack? So how we know about this stack in the data structures, like we have a operations called push and pop operations. We can insert the data into the stack and we can pop that data into the stack. So here the stack is a way we arrange the elements on the top of another. So in the stack we will arrange the input symbols in one by one, like first in first out. So first in first out, we already know about the data structures, how we have to maintain a stack. In stack, how we are going to insert the elements and what are the operations. So here in the stack we have two operations. One is a push operation and second one is a pop operation. So a new element added on the top of the stack. So if it is a stack, if you insert A into this stack, this is called push operation. So here we can say that it is A is pushed into a stack. And when coming to the pop operation, the top of element of the stack is read and remove. So when we have to pop the operation or pop or A, so what in case of two A's are there in the stack, so first one we have to pop this one. We have to read and we have to eliminate that A into the stack. We eliminate from stack. So that is called a pop A. So which one we have to pop in the sense? The first in first out. So in the stack, what is the top element is there, we have to pop that element. So that is nothing but here we have two operations in the stack. So one is a push operation and second one is a pop operation. And here coming to the definition of pushdown automata. So we already know about the finite automata definition. So here we have a 5 tuple notation. In that one we already discussed about the finite set of states and sigma input symbols and transition function, or whether it is a NFA or DFA or epsilon NFA, the transition function is different from one discriminate finite automata to non-discriminate finite automata. And initial is we already initial state, and Z naught we already know about the final state. And the new symbols which are added for this pushdown automata definition, we have a two new symbols which are added for the definition of pushdown automata is nothing but tau and Z naught. So here tau is nothing but a stack symbol. So here the stack symbols which are, if it is a stack, if it is and we also have the sigma which is having the input symbols, example 0, 1. So here whatever we are inserting the elements into a stack, those are all called as tau symbols. So that is nothing represented with the tau symbol. And here the tau is represented as the stack symbol. So in the stack, what are the elements involved in the stack? Those are all nothing but stack symbols. And next one is Z naught. So here Z naught is nothing but initial stack top symbol. So here when we are having empty stack, so initial symbol should be there. So what is that initial stack symbol? In the sense the Z naught, we are representing that with the Z naught. Initially, if it is the stack is an empty, we have to initialize that stack with the Z naught. So this is the seven tuple notation of push down automata. Additionally, for the finite automata, we have two more symbols. Those are related with the stack only. So one is the stack symbol, so that is represented with the tau, and initializing the stack symbol. So the stack symbol initialized with Z naught. So these are the seven tuple notation of a push down automata. And here, what are the terminologies involved with the pushdown automata? So, when we are constructing a pushdown automata, we have to know about this terminology. So, what is this terminology contains? One is the instantaneous description, and second one is the turnstile notation. So, what is this instantaneous description? So, ID, we will represent it with the ID. So, ID of the PDA, pushdown automata, represented by a triple. So here, when we are having the ID representation of push-down automata, so it contains a three tuple. So three symbols. So what are these three symbols? So first one is a finite is the Q is the state. So with in finite automata, we have like this Q0 and Q2 and Q1, like that we have the states, finite set of states. So here also, if a Q is nothing but it is a state symbol. So whether it is a Q0 or Q1, comma Q2. So those are represented with the Q here. And W, so W is nothing but it is unconsumed input. So here in the previous slides, we have giving the input string here. So we are giving the input string to the finite control unit, and that input symbol which is unconsumed input, so that is represented as a W. So the whatever the input string we are giving for the finite state machine, so that is unconsumed input. And S is the stack content. So here S, which is contained the stack, which are the elements which are in case of Z naught, or in case any input symbols are there, we have to represent that entire stack contents in the S representation. So here the ID instantaneous description of PDA, which contains the three symbols. So Q is the state, and W is the unconsumed input, and S is the stack content. So here this is the ID representation. We will discuss it the example how we have to mention the from one state to one state. We are moving from in transition functions, we are moving from one state to one state, and with the input symbol. So how this input symbol is represented in the instantaneous description. And next terminology is turnstile notation. So what is this turnstile notation? So it is represented with the fallen T, and here it is used for connecting the pairs of IDs. So here there is a transition functions from one state to another state. So those are all combined together. We will represent it with the turnstile notation. So connecting the pairs of IDs that represent one or moves. How many moves are there in this transition functions? So we have to represent with the turnstile notation, one or more moves of PDA. So how many moves are there in the PDA? We have to represent all the moves in the turnstile notation. And the process of transition is denoted by the turnstile symbol. So fallen T. So what is the transaction from one state to another state? How it is moving? So that is represented with the turnstile notation. So T is represented one move. And so if we represent ID with the one ID and turnstile, and we will represent another ID. So this is one move. So one ID to another ID we are moving. So that the one move which is represented with the turnstile notation. And the sign describes the sequence of moves. So here one more ID is there and one more ID. So all this represent the sequence of moves in a PDA. So this is about the turnstile notation. So we will explain with the example. So here P is nothing but a transition from P to Q. So here if it is a transition function from Q0 to Q1, Q0 to Q1, so that Q1 or Q0 which is represented in the P, and a B is nothing but input symbol. So whatever the ID which is having the unconsumed input, so in that one we will have an input symbol. So the W is represented, the W which contains the input symbol, that is represented with the B here. And the T symbol, T is nothing but stack symbol. So where on the top of this stack, what is the symbol which is there in this ID representation? So here this T is nothing but it is a stack symbol. So and this is one ID representation. It is moving to another transition function. So these values are changed here. So that according to that, how many moves are there, those are all comes under the turnstile notation. So that is a sequence of moves in a PDA, given PDA. So this terminology we will discuss more in an example. So here we have a design of PDA language for the A power n, B power 2n. So here we have to design a stack symbol. So which stack symbol should be there in the stack and what type of input we have to give, and whether the given input is accepted by this PDA or not, we have to check. So here we already discussed the terminology. It is having PDA, it is having the two terminologies. One is the instantaneous description and second one is the turnstile notation. So here before going to that one, we have to elaborate this language. So we will construct or we will define this PDA with the 7 tuple notation. So we will describe. So P, we are writing P, and in that one 7 tuple notation, the first one is about the finite states. So how many states are there? So here 2 input symbols are there. We will write the 3 states. And so coming to the final initial state is a Q0, and we have a 7 tuple notation. We will write first, we will write the 5 tuple notation. Later we will write the 2 additional tuples. So final state, so we will represent a final state Q2, and initializing and finalizing and transition function. And one more thing, we have to represent the Z0. So Z0 is the top of the stack symbols, and tau symbols. So how many input symbols which are involved in the stack, so which are inserted into the stack, that is all nothing but tau symbols. And last most thing, input symbol. So sigma which is represented, and what are the input symbols? So here A and B are the input symbols. So these are the 7 tuple notation. So we defined with given PDA with the 7 tuple notation. In that one, we are going to discuss about the stack symbols. So stack symbols and initially stack symbols. So here how we are moving from transition function wise, how we are moving from one instantaneous description to other instantaneous description. So here we just elaborate this language and we will write the input string. So example of this input string. So if here we have a n value, so which is greater than or equal to 1. So here if you take n is equal to 2, we will write this language A power 2, B power 2, n. So 2 already, n is there, 2 power 2, 2 into 2, it is a 4. So here we will elaborate this language A, B, B, B. So by seeing this language, we can say that A power n which is followed by the B power 2n. So we have a 2 A's here and B's, 4 B's are there. So here while inserting into a, we have a push and pop operations in the step. So here by consuming all the input, we have to get the empty stack. So then only it is going to be accepted by the pushdown automata. So how this reading and push and pop operation should be done for the stack. So here whenever A is inserted into the stack, so A is inserted into the stack, we have to insert whenever we have to push A into the stack, we have to push A 2 times. So here 2 times we have to push along with the initializing symbol. So and whenever B appears, we have to pop the A. We have to pop the A. So here by this we will explain more in detail with the terminologies with the ID descriptions. So here whenever A appears, whenever A we have to push into the stack, we have to push it twice A. And whenever in the input string, whenever B appears, we have to pop the whatever we inserted. We already pushed some A's, so we have to pop on the top of the element whatever it is, which A it is, we have to pop that A, and we have to pop that A. Whenever we read B, we have to pop A. So that is the logic behind this language. So here we will clearly will discuss about this with the instantaneous description. So we already said that whenever we push A into the stack, we have to insert one more A into the stack. So that is nothing but here we represented. So here the transition of, this is the state 1, Q1. So Q1 is the initial state. So here initial state, whenever Q not appears and Q not appears with the input symbol. So W represent unconsumed out input. So in that one, first one is AA. So whenever A appears, so whenever A appears on the input symbol, so the initially the stack of the symbols which is having the Z or Z naught. So initial stack symbol it is. So here the transition function. So whenever A appears from the Q naught state, it is going to the Q naught state, and we are pushing the A into the Z stack. So whenever input A appears, so I will write. So when initially it is Z. So initially it is Z. Why? Because here in this representation, so top of the stack symbol this one, and this is the A is the input symbol and initial state. So stack Z is there whenever push A. So if you push A into the stack along with the Z, we have to insert A, Z. So this whenever operation push A is there, 2 A's are inserted into the stack. So that is represented in this instantaneous description. And whenever Q naught comma A, so here the one more A is there input, and we will write again whenever we appear in the state Q naught, A appears on the top of the stack symbol, A it is there. So A we are writing. One more A is should be A, one more A along with the Z, A and A and A. So 4 A's are there. So this is the instantaneous description what we discussed. So push A, and here also push A. And here now when we read B, we will change the state from Q0 to Q1. So whenever the input symbol is changed, we are changing that state name. So here initially we are in the Q0, we will write this into the Q1 and start popping corresponding to A. So whenever B appears, we have to pop the top of the stack symbol. So that is represented here. So whenever Q0 with the B input symbol, A is the top of the stack symbol, and we have to pop that one. So whenever the A is there, whenever B appears, A should be popped. So popped in the sense there is a empty symbol is there. So after popping all these A's, we will get the Z, empty symbol. So we will discuss it more with the turnstile, all turnstile notations. Thus, this process of popping B will be repeated unless all the symbols of read. So, when how many B's are there? All B's should be read. So, while reading, we obviously popping that A. into the stack. Finally, after all reading the input symbol, we will get only a Z. So this Z is nothing but empty initially stack symbol. Whenever Z appears in the stack symbols, so that is changing that state from Q1 to Q2. So here if you see this one, Q1 whenever appears empty stack with after reading all the B's, we got the only epsilon symbol, and top of the stack symbol is Z. So Q0 we are moving from state Q1 to Q2 and with the epsilon symbol. So here this is the example 1 which is having the logic behind this A power n and B power 2n. How to insert and how to pop we are discussed, and we will write entire thing in a single representation of IDs. So here we will write this. So we already discussed about the PDA. So PDA, which is having the 7 tuple representation. So first one is about the finite set of states, and these are the input symbols, and these are the tau representation, and transition function, and the Q0 is the initial state, and Z is the initially stack symbol, and Q2 is the final state. So these are the 7 tuple notation of the given PDA. So what is the given PDA in the sense? A power n, B power 2n. So this is the given PDA. For this one, it is the 7 tuple notation. So when coming to the ID representation, so here we will write this transition functions. So initially Q0 is the initial state, and we will write the input whenever A appears, or we will write all together. A appears, Z. So here A is the input symbol, and top of the stack symbol is initially it is the Z. After the A inserting, we have to move to the transition of Q0 comma. So here along with the Z. And one more, after with the Q0, whenever A appears, the top of the stack symbol, so this is changed to Z, A, and whenever again A appears, Z, A, A. So here A is the top of the stack symbol. So here what we will get, transition of Q0 comma A. And again after transition of Q0 comma B, with top of the stack symbol is A. So transition of, it is going to the another state. Why? Because the input is changed. So Q1 comma, we have to pop that one. Whenever A appears, we have to pop the A. Whenever B appears, we have to pop that one. So again what we will get, A. We will write 3 elements in the stack. And again after transition of Q1 comma B, on the top of the stack symbol also A is there. So Q1 itself, and after removing the first, whenever B appears, we have to pop the A. So we have Z. And next transition of Q1 comma B, again how many B's are there? So here how many B's are there? We have, so suppose here A power A, B, whatever we already discussed this elaboration. So whenever we have A, we have to pop this transition of Q1 comma A, Z. So how many B's are appeared? We have to pop all the B's, all the A's. So transition of Q1 comma AZ. We already popped, so AZ. So finally we reached initial stack symbol. So here whenever the transition of Q1 comma, we reached the empty stack initial symbol. So nothing to read here. We will write it as a epsilon, and whenever top of the stack symbol is initial stack symbol is there, Z, and we have to move to the transition function from Q1 to Q2 with the epsilon. So this is the entire summarizing the IDs. So here instantaneous description for this input string. So and we will write the same thing with the turnstile representation by reading all the symbols. So here by the reading this string, we will write the turnstile representation. So for turnstile representation is nothing but IDs. So how many moves are there in this PDA? We have to write all combined together. So here we will write the first one is Q naught, comma A, comma Z. So what is that? When we have A into this one, we will write this turnstile representation, a transition of Q naught, comma A, B. We will write entire thing first. So here transition of what is the input here? We will write a Q naught unconsumed input. So here initially what is the symbols we have, and with the Z. So Z is the top of the stack symbols. Initially what is having the stack contains. So here we will write whenever the input reading A, after reading we don't write this A again, and remaining part we will write A, B, B, B. And so after pushing A into the stack, we will write A, Z. And what is the another turnstile notation? Another move. So here Q naught, comma. So again A is we are reading A, and we are not writing that B, 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 and we are adding those two A's along with A, Z. So I am writing all the stack values. So here what is the stack values entire, and Q naught. So here Q naught B appears. So it is moving to the Q1 state, and we are reading B, B. So after whenever the stack in the input symbol B is there, we have to read the A and we have to pop the A. So here A. So here popping in the sense we have to remove this A and we have to write remaining stack symbols. So here and turnstile notation of Q1, how many B's are there? We have to repeat the same action, same pop operation into the stack. Q1, comma B, B, comma A. Again, how many? One for one B, one A is removed, like that. So I am writing all Q1, comma B, A, Z, and turnstile notation. So Q1B appears again. Q1B appears Q1, and after reading this B also we have empties, and we will get the initialized stack symbol. So here whenever after we have Q1, comma Z, so here with this one we will get so Q2, comma epsilon. So this is the accepted. So the string whenever it is reaching the final state, so here a final state is a Q2, it is the accepted. The string which is accepted by this PDA, given PDA. So this is how we are designing the pushdown automata for the given language. So now we will discuss another example. So here we have designing the pushdown automata for accepting the language 0 power n and 1 power m and 0 power n. So here we will write this one. So 0 power, if you write n is equal to, so n greater than or equal to 1, and we will write n is equal to 2, and we will write m is equal to 3. So for this one 0 power 2 and 1 power 3, 0 power 2. So we will elaborate 0, 0, 111, 0, 0. So this is the language elaborated. So for this language, if you observe this one, so here whenever 0 appears in the string pushdown automata, so we have to insert the zeros, and whenever 1 appears, we have to skip that. Skip in the sense we don't want, we are not performing any push or pop operation, we are skipping the operations, and after once zeros appears, again we have to pop these zeros, then only it is reaching the final state. So this is the logic behind for this grammar. So for this one we have to construct a push down automata. So here we will first write the IDs, so instantaneous descriptions. So here we will write the 7 tuple notation. P is equal to, so here two input symbols are there. So Q naught, Q1 and Q2. So here and what is the input symbol? 0, 1. And if you write here, the logic is whenever 0 appears in the second time after 1, 0 appears, we have to pop the zeros. So here so only 0 is involved in the stack. So what are the input symbols of stack? So 0 comma Z is the initialized stack symbol, and Z naught is the initialized stack symbol. So these are the tau representation. This is sigma and this is a Q, and 1 2 3 4 5, fifth one is initial state and final state, and F, and initial state and final state and transition function. So these are the 7 tuple notation for this given PDA, push down automata. For this one we have to construct a ID. So here, so transition of Q naught 0, whenever 0 appears we have to push 0 into the stack. So here 0, so here whenever 0 appears we have to push that to a stack. So initially the top of the stack symbol is Z, and for this one a transition of Q naught comma 0 we have to insert the 0 along with the initial symbol. So again for this input string we will take a Q naught 0, again 0 appears, and above the stack symbol is here 0. So here 0, and here we are not changing the input value, so 0 0 Z. So after this one Z Q1, again 1 is there. So from 0 Q naught symbol, whenever 1 appears and the top of the stack symbol is 0, we have to skip that operation. So that skipping the operation in the sense, so Q1, Q naught to Q1, it is moving Q1 and we are just skipping. So here we are writing only a top of the stack symbols. So here, so Q1 comma 1, again 0, top of the stack symbol is 0, and transition Q1 comma again. So operation is same. So Q1 comma 1 0, and transition of Q1 comma 0 0 Z. So here we finish the 3 ones, and we whenever 0 appears, so here from Q1 whenever 0 appears, so we have to pop that. So top of the stack symbol is 0, and we transition from Q1 to 1. So Q1 to 0. So we have to write Q1 and we have to pop this 0, and remaining stack symbols we have to write. So here the Q1 comma 0, top of the stack symbol is also 0, and here we will go to the Q1 and Z. So after this one, whenever the empty stack symbol appears in the state Q1, so here nothing to read. So here after 0 and epsilon symbol is there. So transition of Q1 comma epsilon, now it is the top of the stack symbol is Z. So here whenever this kind of instantaneous description appears, transition of this is going to the Q2 and epsilon symbol. So here finally it is reaching the final state. So this string it is a continuous instantaneous description, and these are the IDs summarizing the IDs, and we will write the turnstile notation. So turnstile notations. So we will take the input string is 0 0 double 1 1 0 0. So for this, how to write this turnstile representation? So transition of Q naught comma unconsumed input. So this is the entire thing we are writing. and what top of the stack symbol is Z, and turnstile representation. So here transition of Q naught, we will write all together. So transition of Q naught comma unconsumed input. So after reading this one 0, so 0 left, whatever remaining things are there, we have to write all the things. So whenever 0 appears, we have to push that into a stack. So 0. And next, transition of Q naught comma, whenever 0 appears, again after reading this one, again we have to push that into a stack. So 11100 and 00Z and turnstile representation. So Q naught comma 1. So whenever for reading the input symbol 1, we have to skip that operation. So it is reaching the Q1 and we are skipping that operation and we are writing remaining unconsumed input, and we are skipping the operation in the sense nothing should be added, even push or pop operation. So whatever left in the stack symbols we have to write. Transition of, so how many ones are there, we have to skip all the operations. So Q1 comma 1 0 0 and we are writing remaining stack symbols. So transition of Q1 comma 1, so we are reading this one, so we will get only 00 and skipping the operation, so no need to insert or pop operation. So here transition of Q1 comma 0 appears. So whenever a state Q1 0 input symbol is there, we have to pop that 0 top of the stack symbol. So whatever there in the top of the stack symbol, we have to pop that one. So Q1 comma 0, we have to pop. So if we are popping this 0, we will only get the 0Z. And same operation Q1 comma 0. So Q1 comma, after reading this one, we will get empty epsilon symbol. So no need to write 0. So epsilon symbol is there. So and for this one, for this 0, we have to pop the 0 symbol. So on the top of the stack symbol is only Z. So initial stack symbol is there, and transition of Q1 comma, if you observe this Q1 comma epsilon symbol with the top of the stack symbol Z, so it is reaching the Q2 state. So Q2 with the epsilon symbol. So while reaching this Q2 symbol, Q2 state, so it is a final state. So the string which is the given input string which is accepted by pushdown, this pushdown automata. So this PDA. So given PD. So here the language which is accepted by the pushdown automata. So by seeing this instantaneous descriptions and turnstile notation, finally it is reaching the Q2 state, that is a final state representation. So with this we finished the pushdown automata. We have designed 2 examples for the pushdown automata. So thank you.
Like, share and subscribe. Hit the bell icon for more updates.